Okay, so this is the second part of this. As I said before, this is more questions than answers. So this gives you another different perspective how looking at the interior point method. Go a little bit beyond those what Aaron did. That's good. So this actually is written by Bento, who is also here. Takashi, Tsuchiya, and Wei. I call this as interior point part 2. Okay, so I would say there was various solutions of solving LP. Okay, so one is called approximation algorithms. One to get a solution is almost optimal, almost feasible, and the negative part is also very, very small. Okay, that's kind of epsilon analysis. But there was another algorithm, so we really want the epsilon equal to 0. It's like typically in the real infinite motion arithmetical operations, for example, simplex method, which we call the exact algorithms. Okay, as long as you carry out your intermediate solve system linear equation exactly, you can solve linear programming exactly. There was some other algorithms, which is actually dependency on epsilon is very low. It's called polylog 1 over epsilon. Okay, so ellipsoid method again is iterative procedures. Okay, interior point also belongs to one of those kind of things. Okay, so if you apply interior point algorithms, really want to solve a linear program, very, very high accuracy, usually people do so-called crossover. So at a certain point, you identify which constraint is going to be active, which one is inactive, then you move to a Kohler solutions. So actually, many interior point algorithms implementation in commercial solver, they have a final phase, it's called a crossover. It's try to finding a Kohler solution, because Kohler solution is more combinatorial, whatever. For solving integer linear program, you really need to get Kohler solutions. Okay. But also, of course, nowadays people don't care about high accuracy. You can also analyze algorithm to solve linear programming. You don't need log 1 over epsilon. You only need 1 over epsilon. So many notion of a first order method, gradient projection, all this has come out. Okay, so either on I'm going to emphasize on the high and the exact algorithms, because this is what strongly polynomial time algorithms play the important role. It's like those combinatorial optimization. You really get, your object is the combinatorial sense, either yes or no, whatever you need to answer. Okay. So improvement over this polynomial solver for LP, as I said, actually strong, and yeah, it's not which is log 1 over epsilon. I just wanted to mention, if you omit this one, of course, this is built on the Aaron and Lee, and also I think this is more based on using volumetric center, okay, stuff, and also with the faster, linear the basis and solver stuff. Okay. So there's also now, is that right? Bento, you tell me whatever. So now you can reduce this to n to the omega. What's the omega? It's like a matrix multiplication, those magic numbers or something. I don't know. Okay, it's the theoretical things. Okay. Of course, they also have nm plus m 2.5. Is that true? Okay. Yes. So this is a most recent paper and this. Okay. So all this is operations, but there was log 1 over epsilon. Okay. Okay. So that's the matrix multiplication experiment. People have all different ways to do this. The lowest one is like a 2 point something or something. Anyway, so I will. So this is current progress. You can follow it. What I'm aimed is more on those exact algorithms, okay? Because my last dream is to see if we can really answer that question. So LP have a strong polynomial load. Any approximation algorithm does not do it. You have to find the exact algorithm. The algorithm has to be combinatorial. So to answer that question, so let me just bring some kind of so-called scaling invariance in LP algorithms. What is the scaling invariance? Take any positive diagonal matrix. You scale the variable by saying does not change the problem, right? Okay. So you scale your C by D, you scale the A by D, and also this same thing. So you basically do these kind of things because D is strictly positive. So at the basic solution, those positive still positive, those zero still equal to 0. Okay. So algorithm is called scaling invariant if it generates a geometric identical sequence when applied to P and D and after scaled. So when I say scaled, it's after you scale back, give you the same sequence. There was some advantage method to be scale invariant, okay? Because you know maybe have a scale invariant and the algorithm is very stable. So in these seconds, simplex algorithm is not a scaling invariant. So if you scale the problems, for example, for clean binting algorithm, you scale some problem, the problem actually becomes nice. Of course, so you can feel some kind of a scaling D as a preconditional or something. But of course, to find the best precondition itself is the hard problem. But other algorithms, for example, is called the predict correct algorithms. So this PC developed, it is a scaling invariant. This is due to the Newton method. You can do this kind of things. So recall what is the the predictor I already talked about in half hour ago. So I'm not going to do this. So standard analysis say before decrease mu by a factor of 2 in square root n iterations, basically. Yeah. And another nice thing about it, you can prove this MDY algorithm at the final stage when they get close. They have so-called quadratic convergence. I don't know. Have you know what it means? So when I said the central path converges to this to some points. And very far away, our mu k plus 1 equal to gamma times mu k. As I said, gamma is some kind of a fixed constant. Okay, so we call it you can geometrically decrease mu k. But you can prove at a certain stage, you can take mu k plus 1 equal to mu k squared. And mu k is small enough. That's what the predict correct algorithm can do. They proved at the beginning you only have a geometric consequence. At the end, it will do according to these fashions. We usually call this as a quadratic convergence. So if you have an algorithm like this all the way, you only need double log 1 over epsilon. The reason is because we know at the final stage, the central path will be very smooth. Okay, so that's the one way. So the smoothness comes from here. So that's what, and also the algorithm is scale invariant. You have this one. Yes, question? Okay, yeah. So this is how. Then, how to analyze the central path? In the past, we come out with different condition numbers. Okay, I'm going to list two of them. Okay, one is related also to simplex method. Let B be a set of index of column for A, and let AB, those columns constituted by A sub B, be a subarray associated with B. We assume this matrix is linearly independent, so they will be invertible. Okay, so then, yeah, you don't have to be all invertible. Take those invertibles. The condition number kappa A, kappa bar A is defined as kappa bar A equal to max B such that AB inverse A. So this is just a matrix norm. Okay? So you can think about the inverse of AB against all other way. For example, if this A is randomly generated, this number is bounded by n or something. Okay. But however, we have to take maximum on all the possible bases. Okay. As you can see, this is a scale invariant. Yeah, basically say if you scale this matrix, redefine among the scaled matrix, it's not equal to A bar A. However, to make it scale invariant, you take all the positive diagonal matrix, finding the infimum ones. Okay. So this is this is scale invariant. This is scale dependent. So this two condition number somehow. But another thing is this two condition number only depend on A. Okay. So what about the exact argument? Depend on this one. Okay. So this is introduced by Dicking and also some Todd, still Vavas, yeah, and Terrell's stuff. So here's the theorems for exact argument. As I said, I departed from those approximation arguments. So LP of the form in this standard form can be solved exactly. This is exact. Just like a simplex method. Each iteration you do solve system equation, assume you can solve that system equation exactly. You find a solution in n 3.5 log chi bar A steps. It's many iterations. Each iteration solves a system linear equation. Okay? So, first, this iteration complexity does not depend on B and C. Only depend on condition of A. So that means you have algorithms. As long as A is the same, doesn't matter how you construct B and C, you can still solve this by this above. You can make B and C arbitrarily bad, okay? Arbitrary length, what kind of things, crazy numbers, doesn't matter. Okay, this argument probably rings the bell to you. Is that in the old days, Avocado has a paper, right? You can solve linear programming with running time is independent of B and C. What he did is he constructed a sequence of linear programming and rechange B and C and resolve that problem. Basically, for any linear programming, you construct some kind of length of A, you can reconstruct your BC whose length is no more than length of the A matrix or something. Then, so the overall, because the polynomial complex depends on the L, depends on the bit length of A, B, and C. Somehow he reshaped the B and C whose length is also proportional to A. So then you can solve that problem. The whole length is only dependent on A. But in the middle of construct this sequence, you need to do some computational work. First, you have to really compute what's the length of A, whatever. But with these algorithms, you don't need to do it. It's the single loop algorithm. So you just go ahead. The algorithm will be only dependent on the kappa A. Okay. So the T technique is the departure from so-called affine scaling to the layered least squares linear system solver. So this algorithm depart from the standard linear programming problems or MTY algorithms. This algorithm actually is scale dependent. It's not scale invariant. Okay, it's depending on how you scale the matrix. As I said, scaling could be a good thing, could be bad thing, but could be also good thing. If you know some knowledge, you can scale in to make it this condition could be make them better. So anyway, so this is one thing. So let me just, what is the basic idea? As I said, the basic idea, we know what's the affine scaling, okay? Each time when we have an X, we have to, find one such that, have X use affine so-called scaling. What this layered scaling is, they don't directly use the Xi. They have some kind of a priority. First, they check the solution. The solution may be split into a big part, relatively close. Another layer, this layer relatively close in terms of the value, but it's substantially different from this one. Okay? Usually, if you have an algorithm solution, like a Clementi or some problem, always have this structure. Or if solve MDP problem, deterministic MDP, those variables on the cycle have a very big magnitude with discount. Some of those not on the cycle, deterministic MDP, so basically finding a minimum cycle. Some not on the cycle, some on the cycle. On the cycle, they have a big layers. On the not on the cycle, they just equal to 1. So what we do is, we first finding a least square, do affine scaling on this one, find what's the best solution. We fix that. So that affine space is fixed. Then we do a second layer. So this whole process is still like affine scaling, still like a scaling, but some scale have an infinity. Some you have to do first. Make them sure they have a very good projection first. It's called layered least squares. So automatically take care of this. So the key idea is you can prove the central path for given linear programming problems. They have an n-squared short curved segment of length only related to this condition A, X kappa A. Relatively smooth. So for those part, reduce from mu to this mu, you only need this many iterations. Okay? Then we further prove this sharp curved turning point, or you call it kink points, can appear no more than n² times for any given linear programming. So you can think about linear programming is composed as n² relatively smooth part. In those parts, you can take a very large step. But however, to get around of this, You really need many line segments to do this. Okay, so that's the chi-bar A, which is constant. So no more than n squared, take that much to get a 1/4 point, to take this much. And so most of this computation is try to get around these corners. Okay, yes?
Is it missing an exponent out there? Chi a to the n on the first sentence.
Or length of n, yeah. Oh, yeah. I think it's n, yeah. So that's why this n comes when you take a look. You are right, I missed the n over there. So there was n over here. So the n is over here. You are right, thank you, yeah. Okay, so it's like from here to here, you need this one. Actually, majority of this is suspended over get this one, okay? Then from here to here, you get another one. But this comes to sharp 10 no more than n squared times, okay? The algorithm is not scaling invariant. Okay? So the question is, the future, some of the work is try to get this scale invariant improvement. So the original algorithm is dependent on chi-bar A log n 3.5. This is Montero Tuccia 2004. They said, oh, you don't need to do this. You just use the analysis from this Vavas's paper. You just directly analyze this, predict the correct algorithm. You can prove your algorithm is bounded by n squared log 1/6 and n 3.5 and this number iterations. And this condition number now is chi-bar star, which is scale invariant. I already told you. So this one is the one, yeah. So this one, this number is always smaller than this. Because it's the infamous among all the positive scaling matrix. If you can scale matrix arbitrarily, you get this one. The log 1/epsilon here, yeah. So this is basically say, in those very piece called, you can reduce mu by mu square, basically in that piece. You only need to get around of the sharp top by this much. You can like n square. So chi-bar is raised by kind of scaling invariant. Okay, here's comes the 20 paper. Okay, this is I can include it. You can solve this exactly by n 2.5 log chi-bar star A, which is the smallest one, which is scale invariant. So basically, they create the scale invariant, which is you only need the linear system solver. It's still like a 3.5, but however, you become the scale invariant. Okay? Now the question is, how good are those numbers? You immediately see this. If those condition number bounded by polynomial in n, you're done. You solve, you answered the question. You can find the strong polynomial time algorithm. Okay? Well, unfortunately, and so far, nobody be able to prove it. If you're only based on central path, that chi-bar A cannot be bounded by polynomial in Mn. So in some sense, in APN, according to this kind of a path-following nature, it's very, very hard to turn this into a strong polynomial.
So there are examples where this is
Yes. Okay. So the key question now, how curved is the central path? If they only have an n squared, okay, relatively smooth path, if that smooth path condition number is still very good, then you can because the curve, the big sharp turn can no more than n squared is already put for central path. Is the relatively smooth part, can that be coverage still only dependent on how smooth, basically, only on that smoothness can without the chi bar A, those condition numbers. Okay, so this is the questions. Okay, so the sharp turn is very hard to manage. You can think of why they can make a sharp turn. For example, you slightly tilt the objective, then you make this straight path. For example, sometimes the central path should be, for example, you have an objective like this, almost parallel to this one, right? So in your early stuff, you're far away from this hyper constraints, your central path is almost like a vertical line. Oh, now at this point, when they get very close, oh, this objective is slightly tilted. Actually, it's the only optimal solution over here. So this is what we call the sharp turn. And this cannot be appeared more than n squared times. Okay? The central path is also behaved like this type of things. This also applied to Clementi computation. So, how many ways to solve LP exactly? Can the condition number be bounded to polynomial integrations? Because the sharp turn is no more than n squared. The only left is those relatively smooth part. Can they be entirely dependent on them? So this is a question. Unfortunately, this is so obviously from the geometry you can connect this to so-called coverage of the central path. So what's the coverage? As we said, oh, I changed the mu to nu, whatever. It's the same thing, parameterized by nu. This is a central path point. Okay? So what you can do? You can define this number, nu, okay, times x derivative with respect to nu, s derivative nu, take product, okay. Then you take an integral from initial nu to a final nu. Let's say from initial 1 to epsilon. They define this to be the coverage. Basically, if you have a central path like this, you basically integral the coverage among all these lengths. Parameter View is well defined. This is the people how define a path to be the coverage of the path. Okay, so it's already proved. Okay, the iteration of central path based linear program algorithm from initial mu to final mu is almost equal to this coverage divided by square root of beta, where beta is the neighborhood width. So what's that? The other way is basically say the complexity, how many iterations need to implement the standard interior point algorithms. The worst case is basically dependent on the coverage. Okay, beta is some kind of a constant. You can be sure this coverage, if you remember, this is number of algorithms is bounded by this one. Because the interior point is scale invariant. So here, chi bar A is chi bar star A is that condition number. So basically say, what happened is say, the coverage log chi bar A, the difference is by astronomical polynomial numbers. If you can prove this one is astronomical polynomial, then you're done. Okay. You can also rigorously represent it by some kind of differential geometry quantity. So this is a group of people and also using information geometry. So basically everything boils down to coverage. of the central path. Now you can say which linear programming, at least use LPM is polynomial solvable, which one is not, by this condition number. Okay. Of course, you don't need to be compute this condition number exactly. People say you can approximate by n factor. That should be also good if you can prove something. Okay. So here's some things. How many they need to go from polynomial? Okay. And where's inside the neighborhood depend on this coverage here. So this is related to the coverage now. So lower bounds. Okay. I think people now start construct an example to make that coverage arbitrarily bad. It turns out you can, the coverage, we call the Clement instance, is exponential. Okay, so if you take a log of the condition, actually the original condition is double exponential. Take a log, still exponential. So that says the standard IPM cannot turn this into strong point. You do have instance, type A is double exponential. Take a log, still exponential. Okay. So this number construct many cards, but there was another one which is the very recent limit. I don't know, Aaron, you know this paper? Or? Yeah. So this paper, I really want to try to analyze the exact algorithm to see if you can bound that condition number. So you can construct an example. This is the polynomial. So this example, you need to construct the dimension of the problem is very, very small, but you have to add the exponential number of constraints. So this is an example, which is n in number of constraints, only is polynomial in the dimension of the polytope, but however, still be able to prove that double exponential condition.
I forget, was this for other barriers as well, or only?
No, this is only analyzed on the central path.
Okay.
Yeah, there was no other barrier. I would be interesting questions if you can prove this bad example still happens to volumetric center problems. Yeah. So this is called all based on the central path, which is standard analytical central path. Yeah. So this is lower bound and all these problems. Okay. So this really want to to solve this problem. Okay. So basically say another one which is given by this group of researchers, as I said, Taduchi and those people and those 4 people, and they really want to, then they developed another different notions called the straight line IPM complexity. They called SLC. So they basically want to see, give any curve, then they define a neighborhood. What's the minimum number of line segments stay in the neighborhood? Then from the mu0 to mu1. Okay. So you can imagine, because all the interior point methods, they create some kind of a straight line, right, within neighborhood, somehow still close to central path. So the question is, functionally, within the neighborhood, what's the smallest number of piecewise linear functions? You can approximate that curve, still stay close to that curve. So they count this number, find this number actually is very closely, again, related to the classical interior point algorithms. Okay, so basically say for anyone, if you can find a minimum line segment within the neighborhood, or some neighborhood defined, the interior point algorithms can almost follow that line segment with no more than n1.5 times some kind of eta actually they represent for some tightness of the neighborhood or something. So basically say, of course, for linear program, if you don't consider neighborhood, you always have a single line from initial point to the optimal solution, correct? Because if you don't restrict it to be close to some kind of a path or central path, that's the nice about a convex region, right? From any given point, you can directly see what the optimal solution is, because that strict line is still in the feasible set. So the question now, in order to finally resolve this question, develop a strong polynomial diagram. First, you have to maybe develop different notion of a path. Maybe a volumetric central path or something, I don't know, okay? Okay, another one is how to define the neighborhood of the path. Because if you have a neighborhood arbitrary large, the line segment will become smaller. If you arbitrarily large, you can always have a single line from initial point to the optimal solution. So that's the something which is what maybe people, you can think about it, okay? So every rhythm element traverse these only numbers, okay? For example, we have this one. So basically, again, unfortunately, right now, the central path cannot do the job. We already have a bad examples. Okay, this is for exactness analysis. For like a approximation analysis from 1 mu, I said that we already have an n cubic root. So interesting. So this is all basic, give lower bound. How good the IPM could be. So now let me summarize which problem are strong polynomial solved for now. Okay. So far, we based on analyze condition number, or you prove simplex method can do the job. Unfortunately, we cannot say claim. So you know this is Steve Snail posed this question, right? And this is a century math question. So strong polynomial known before 2002, shortest path. It can be formulated as LP. It's combinatorial easy. The export on those kind of things, of course, that's strong polynomial solvables. Okay. Bipartite matching and already probably also all of these things, maximum flow and all this minimum cost of flow, minimum commodity flow, lattice polytope, and all these flow. So some of these algorithms actually have a specialized algorithms. Okay, may not be proved by interior point algorithms. So this is another picture. Some of those combinatorial algorithms are sometimes better than general purpose IPM method. IPM cannot prove strong polynomial. Okay, of course, for combinatorial LP, so basically you can prove the condition number or something bounded by 2 to the polynomial. Then you take a log and then become log. This is the condition number. Maximum generalized flow. I think this is approved by Rich 13. Okay, so they, I don't know. two variable feasible systems. So each A, this is I think this is eventually by Megiddo already proved. Again, some of them is non-IPM. It's not based on interior polynomial. Okay. Discount MDP, and so this is as long as the discount is fixed. MDP, I don't know, infinite horizon discount MDP have a linear programming representation. Okay. You can prove simplex method, policy iteration method is strongly polynomial, but we cannot prove IPM is strongly polynomial. Okay. There was a very, very nice extension by Professor Zivik. Okay. Use this technique and to apply to strategy iteration method, right? What's the strategy iteration method? Which is your MDV have a two set of states, one state maximize, another state try to minimize. You have a value iteration method, but however, nobody knows for that discounted, they call the stochastic term-based game. Okay, problems. You don't have an LP representation. Actually, the problem is not convex. But amazingly, you can prove with discounted, as long as discount factor is fixed, you have a strongly polynomial time algorithm. But the original problems, you don't even know whether it's NPU or not. Again, that algorithm is not based on IPM. So I just want to know. So sometimes I really want to solve these problems. And also deterministic MDP, regard discount. You don't need to do discount, okay? You prove simplex method is a strongly polynomial. This is a special case of linear programming. I know simplex method definitely beat the interior polynomial algorithms in the worst case.
Are there other methods that will give you strongly polynomial, or is it only method no?
I think there was other algorithm also give you a strongly polynomial. Okay, but for this SDP, so the natural question is, can you? So we will talk about, can you solve deterministic zero-sum game with a strongly polynomial time, right? I think this is still open, or like a parity game or something.
Yeah, so sometimes called the mean pair of games.
Mean pair.
That's still also open.
Still for nobody's can prove this is belong to NPR, but at the same time we have not found it. So it would be nice to crack those problems. But I know for if it's not game, you can solve this one. You can use simplex method. So whether you can do or not. So this is some questions. Okay. So small dimensions, of course, you can do this, randomize the simplex stuff. Okay. And yeah. So this is of course, okay. So you can do this. Again, Clemented, okay. No self-concordant barrier is strongly polynomial. Basically, again, interior point algorithms, even all the possible barriers, if you consider different barriers, universal barriers, doubly exponential. They are exponential. So this is also, which is not of a negative result. Okay. So anyway, ultimate questions, if Markov decision discount number arbitrarily goes to 1, whether you still have a strong polynomial time or not. Of course, the problem can be solved in polynomial time, but what about the strong polynomial? Can you prove condition number for that problem somehow independent of gamma or something? So this is also a potential in the sense which you can look at. So my hope is, if you want to prove whether there was strong polynomial diagram for LP, you better prove if there was a for discount market design. In general, undiscounted case. It has a lot of nice structures. Okay. Deterministic can do it, but however, in general, we still don't know how to do it. I think that's most I want to convey to this audience, okay, or called mean cost generalized flow or something. Mean cost flow is good, but generalized flow is good. Anyway, LP remains an open research field. Although it has been studied for centuries, somehow still have a lot. No, if you are a student, you can choose working on LP or do ChatGPT or something. You decide. So, okay.
Thank you. Questions?
Yes.
So does the potential reduction algorithms that
Yeah,
you described previously also fall
that's
into, like,
exactly.
they follow the L infinity norm neighborhood
Yes.
of the central path?
That's an excellent question. So as I said, if you really want to prove condition go beyond that central path coverage, you have to redefine your central path or redefine the neighborhood. I don't know. Maybe potential reduction. Maybe give you a different condition number or something, because you go a little bit further away from the neighborhood. So its potential neighborhood give you even better cover, like those condition numbers. So you can use the last number piecewise linear function, still within the level set, but use much less number of line segments. Yeah, so that's the mystery. So all this negative result for IPM, interior point method, is all based on analyzed coverage of the central path. So I think the first things you can do is find that example for bad, they have a very bad coverage, to see how the potential level set looks like. Is it relatively smooth or whatever? You can use much number of line segments, still prove from one potential jump to a different potential, jump to a different potential. Just keep the equation.
Any more questions? All right, let's thank Yinyu again.
Okay.
All right, so that concludes the bootcamp. Just want to do a few quick thank yous. Thank you very much to all the speakers this week. Thank you to the Institute for all the help over the week, and to the other organizers. So thank you all. So yeah, have a